Good day, guys. How are you doing today? So for our previous lecture, we start 7-segment display using binary data. Now we want to make use of the hexadecimal, the BCD hexadecimal number. Now, so that it can be easy and can easily manipulate them. Now let's see how it's being done. In our previous code, we have a code like this in this form. Okay. Sorry. What I've done here is that I have added 16 bits. Here I've created a file called remote port with potentiometer. Then I've added this is for 3F. This is the hexadecimal number equivalent to this. Let me show you my binary equivalent number to this. If we see the binary equivalent, this is 3FA as well. If your A starts from the back end, this is my F, this is my G now, this is my A. So, sorry, this is my, if A starts from the back end, so that means we are going for this. We are going for this, but there's a way we can also alternate them for common anode. This code will work for common cathode. That means the first aspect of this, where our A will start from here, but there's a way we can manipulate them and turn off the bit of this, of the other one, to maintain the same status quo for both ends. So we can just change it by turning off the bit by negating them. Now, how do we do it? Now, for example, let's focus on this. So we assumed our A start from here, A, B, C, D, E, F, G. Understand? 3F means what? For instance, if we check our binary representation for the previous code, we have binary representation of this common cathode. Understand? So this is 7 bits, right? For the BCD means okay, for instance, for our BCD, we can add something like this. BCD for something of this, let me come in. Okay, let me just, I'm looking for the, okay. Test being, we have 1, maybe for example, we have 0, 0, 0, 0. Then we have 1, 1, 1, 1. This is 0. This is 0 help, right? This is 0 help. But in case this one is what? 1. We have this is what? 0, 1 in BCD form, 4 bits. That is 0s 1. Sorry. 1A. This is BCD rep. This is 1. You group them in group of 4, and the other one also in group of 4. This is 1, unlike normal binary. But this is 15. In binary, okay, to write 15 in binary, that is this is in binary 15. To write 16 will be in this form. Maybe 1, 0. This is 16. But in binary, in BCD will represent each of the digits in 4 bits separately. So in 16, the 16 here will represent what? That is 0x 1f. That is 6, but which means every digit is represented individually. This is 15. That is what? This 15, right? The other one also we have this, right? It's 16. But that if you want to make it, will be 1, 6, for instance. 1, 6 will now be, that will be 0, 1, 1. So yeah, 0, 1, 1. This is 6. This is 6 in 4 bits. This is 1. This is 1 now. Ordinary 1. In case of 26, 26 will just be 0, 2. That is 0x. 2 will be what? That will be 1, 0. 20, maybe 27 will be what? 0, 1, 1, 1. This is to be 27, 2 and 7. 2, this is the 4 bits. The rest is the remaining plus digit. So these are the decimal values. So that is how they are represented. So coming to our normal code here, we also have, this is A, B, C, D, E, F, G, right? This is A, right? This is 7. To make it 8, we have another 0 to it. To make it in form of 8-bit, we have another 0 to it. Then we now have the first 4. Maybe this is this one will be in form of, the first one is F, right? 3 represent, of course, you can go alternate them. That will be 3F. This is F, this is 3. So it depends on our arrangement of the pins. The pin arrangement. So that we have 3F. That is for common cathode. That is for common cathode. But let's try it here. Let me see the last one. Okay. We have a 3F here now. So, but my own is in common cathode. I arrange the pins. This in common. The circuit design is, I've changed it to what? Anode. To be in anode there. So the first pin goes to the first pin. The second pin goes to the second pin. Top pin goes to the second pin. And this is in common anode. I've taken it out, not to be. Can you see? I've taken it out. It's not common cathode. So common anode. Now, let's go on. Then we have the B now. This is our hexadecimal values A, B, C, D, E, F, G. But this is common cathode configurations, but we are still going to convert it to common anode. Now let's loop it. Let's come to our display button. We are used to this number in the common cathode where we have it what in form of this, and it will work for us. Then common cathode. So you can do the same. You can do the same thing, and it will work. But if it's not working, but it's not going to work yet itself, because we still need to what, create another value here, and that value which we change the code. We configure the code and call int pattern. Let's name it as pattern, and name is our what? Let's call our 7-segment value here. This one work for the binary straight, the multi array. This one will work directly, but to you make it for the hexadecimal, let's pass the number, the index number to this. Once we pass the index number, we're able to get the number we are working with. Then we pass the number to it. So we're able to get the index of maybe index 1, index 2, index 3. Then we get the pattern. So now we replace this number here with pattern. Then we now shift here. So still, we are still in common anode. But to make it common cathode, we toggle the bit. You will see that the bit toggles. That makes it what? Common cathode and common anode. The bit will toggle. So then you can see 0 patterns, 0, 0, 0, 0. If for instance again, let me come to our, sorry, incoming, I'm putting this thing out. Then for instance, we have this. Okay. So you add, sorry, I'm coming. Oh, delays. Oh, sorry. I'm looking for boss. Okay. I have something like this. 8. This is 8. Ctrl Z. Then I will now use standard. Then we have 8 here. If this is for common category. For example, if this one is A, B, C, D, E, F, G. Understand? Then for this one to be, or this one will be grounded for common cathode. When 0 is 1, it be grounded. That's common for common cathode. So where this one will be grounded, so that means all these pins need to be 1 for it to make a connection with the grounded one. But in case of common cathode, or instead for common anode, it has to be in form of VCC. That means all this one will be 0 for it to be applied what? with 5 volts. With 5 volts, with 5 positive 5 volts, for instance. 5 volts here. So all these things will be 0, 0, 0, 0 for the perfect connection to turn it on. So it's when it is 0 that these are LED. Our A, B, C, D, they are all LEDs. So for any of those portions to be on. So then, now for us to this take on cathode configuration to change the bit, the result of this can either be 0 or 1. So it is 0 and it's passed here. For cathode, for anode, we just add the what? The exclamation mark to it to turn it off. We want the opposite, not the number one. We want the opposite version of it. For instance, if we just look at it, let's first leave it. Let's now run our code. This is to 16. Let's compile this. Compile. We have issue with this. Okay. Compile. Then we open our reload. Let's load it. Load firmware. Okay, then port rebuild 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A, B, C, D, E, F. We have not done something. We don't export it. We just compile. We compile. It's still running this demo I did. Export compile library. After exporting the compile library, we come to our code again. We reload it, and then we run it. And see, we are seeing something else, which is not what we are expecting. Let's change this to common cathode. Let's run it. It's now coming on. Common cathode is not working here. So we have to redesign this cycle. That means the cycle needs to be redesigned. But let's run it for the common cathode we run it for. That is it. That is a common cathode. Let's change the bits. Sorry. Change the bit here. Oh. Sketch. Export compile library. Then we have reload. We have to change it to common anode. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we do it that way. So now let's test it in the other microcontroller here. So let's load our, let's reset. Then let's come to module, spare parts. Okay, we already have what? Let's delete this. Let's get our 7-segment display. Let's change this to 1. Let's change it to how many? Single. Change it to 1. Then with what pins are we configuring? 2, pin 2, pin 2, pin 3, pin 4, pin 5, pin 6, 7, and where is 8? Pin 8. Then we don't need the decimal number, so we okay. So we now, I think we've not changed the properties to be, that is a common cathode. Let's make it low. 3, 4. We are sending low signal. 5, 6, 7, 8, 9, 10, 8. Oh. Then we load this. Reload last. Reload 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, B, C, D, E, F. That's nice. Then we now, okay, the last thing we need to do about it is to make the workpiece. Is with potentiometer, not to just bring our potentiometer here. And let's connect to our pin. We take this one, go to our VCC, and the other one go to the ground. I just do it this way. The GND and the other one go to the VCC. That is go to the 5 volts. I just do it this way as well. And this will go to the anode. The A0, A to 5 are the analog ports that we can use to read our analog values from our system. So we don't want the information to be displaying. We want to turn on the knobs by ourselves. So then we come to our code again, just little modifications. What do we need to bring in here? We need to bring in again our port, communication port, the port in which we constant int port pin, potentiometer pin, which is A0. So then I'll come to our mode here. Then pin mode, that is pin, port pin. Then this is what? Input. So it's input, so it's not an output. Because want to receive something, information from it. That means the other part is okay. Instead of the information here, we want to comment this. Now let's read the port value. Import value equals the port value is we got to get the analog read. Analog read, which pin? Port pin. So we are reading the value from the port pin, then int readings. You get our readings from map is a function we explained in the previous video. So also explain this, that's port value from our ADC. ADC is 10 bits, so we move from 0 to 1, 0, 2, 3, 10 raised to power 2 raised to power 10 minus 1, 1024 minus 1, 03. So it complete from 0 to that. So then how many bits do we have here? From 0, we are going to 16. So that is 1, that is 0 to 16. We're going to stop at 15, but 0 to 15. So then we terminate the value here. From there, we now get the value. We now begin to read the value here. Display int reading. Then we delay for 1000. Then compile is working. Export the sketch. Export compiled binary. So we are good to go. Reload last information. Then we have, this is 0. So we have 0 values. 3, 6. I see B. I see. We get the result here. To tell, you can also bring out your serial monitor to get the information done. So you can also bring out your serial monitor. So serial terminal, is this serial terminal or serial monitor? Yeah. So this is your serial terminal. So your receive, go to the transmit button. And yes, that's I think should be fine now. So you can just double click this. Okay, then we have our value this way. The value display here, so we don't even need this. Then we just come to our code, just make a few changes. Serial communications, from our previous video, we also explain what it does. So just from our setup pins, just get with serial.begin. Serial.begin. From our baud rate, I start on 600 baud rate. That is standard value for serial communications. Then we have our, from here, we can get our value here before display. That is serial, right? So that's all reading. Then we compile the code. We export the sketch. So then we reload we reload this. So sorry, let me reload this. Reload the firmware. Then you can see we are getting the value here, but in ASCII form. Let's make it hexadecimal. 07. We're in 07 already. Let's move it down here. Right, 0 is 14E. I see. So we are getting the result. So thank you very much, guys. So I think any question, you can also try it also with the virtual terminal on the PICSimlab. You can also bring it down and display the value you wanted to show. See. All right. Thank you very much. Have a wonderful night, sir. Bye-bye.